So section 4 is on effusion and diffusion, diffusion, effusion and diffusion. So I'm going to start with Graham's law of effusion. Does anybody remember what effusion is? I think I talked about it last year in bio. Did I? Maybe I didn't. I don't know. Anyway, okay. Effusion, which you can see from the picture on the bottom right corner. It is, hopefully you all remember what diffusion is, right? Do we all remember what diffusion is? Anybody?
Moving the molecule.
Yes.
Yeah, moving molecules from what to what?
High to low.
Exactly. Perfect. Okay. Yeah. Moving molecules from high concentration to low concentration. And effusion is just diffusion through a tiny hole. So you can see here, you've got all of these particles on the top. You've got a little hole there in the middle. And then effusion is just basically the particles moving through to the other side through that hole. Now, effusion and diffusion are going to both depend on the speed that the molecules are moving at. So the faster the velocity of the particles, the faster the rate of effusion and diffusion. Now, speed is going to depend on two things. It's going to depend on temperature, of course. We've talked about that with the gas laws. But it's also going to be inversely proportional to the mass of the molecules. So what that means is that the larger molecules are going to move more slowly. So in physics, I'm assuming last year you learned the formula for kinetic energy, which is 1/2 mv squared. So for two gases, A and B, that are at the same temperature, we're just substituting, those should be lowercase m's, but anyway, half of the mass of gas A times the velocity of gas A squared is equal to half of the mass of gas B times the velocity of gas B squared, right? So MA and MB are the molar masses. We're going to get rid of the fraction by multiplying both sides by 2. So that gives us MAVA squared equals MBVB squared. Now we don't like that square root because if we want to compare the velocities of the two gases, we have to arrange the equation to give the velocities as a ratio. So if you want to compare how fast gas A moves compared to gas B, then you rearrange the equation, you get VA squared over VB squared equals MB over MA. Does all of that make sense so far? Just kind of a bit of algebra, I guess, rearranging equations and such. So basically we're just taking the VB and we're moving it down here and MA, moving it down there. So we can isolate the velocities on one side so we can create a ratio. Finally, we're going to take the square root of each side and we get this equation to compare velocities of gases, which is VA over VB equals the square root of MB over the square root of MA. So the velocities of the two gases are inversely proportional to the square roots of their molar masses. That's just a written description of the formula. Because the rates of effusion are directly proportional to their molecular velocities, we can write the rate of effusion of A over the rate of effusion of B is equal to the square root of the molar masses B over A. Okay, because rate of effusion is directly proportional to velocity. So we're just substituting rate of effusion for velocity. So this effectively is Graham's law of effusion. The rates of effusion of gases at the same temperature and pressure are inversely proportional to the square roots of their molar masses. Again, just a description of that formula. Graham's experiments dealt with the densities of gases, and we know that density varies directly with molar mass. So the square roots of molar masses from the equation can be replaced with the square roots of their densities. So we can replace the molar mass with density because we know that they are directly proportional. So this is just like different versions of the equation, depending on what kind of information you're given in a practice problem. You can use the rate of effusion is equal to the square root of their molar masses, or if you're given densities, you can use the rate of effusion with the densities. So let's do a sample problem. Compare the rates of effusion of hydrogen and oxygen at the same temperature and pressure. So the first thing we do is we analyze the information that we're given. We're given just the identities of the two gases, which are hydrogen and oxygen, and they want us to find the relative rate of effusion. So what we're going to do is we're going to take the molar mass ratio, and that's going to give us a ratio of the rate of effusion. And we're going to use Graham's law to do that. So they've given us the identities, which means that we can use the periodic table to calculate the molar mass. And using that, we're going to find the ratio for the rates of effusion. Keep in mind that whatever gas you have on top for the rate of effusion has to be on the bottom for molar mass because they're opposite. So we've got the molar mass of O2 is 32 grams per mole, and H2 is 2.02 grams per mole, and that gives you a ratio of 3.98, which is basically 4. So that means that hydrogen effuses 3.98 times faster than oxygen.